Yeah, I logged on.
All right, so we're in week 8. This week, got an exam, be open this afternoon, and closes on Tuesday. I'm going to do my best to get through Chapter 8 today, and I think it should be fairly straightforward with oil and gas engines, and hopefully we all have a fairly good grasp on how they work. So we'll cruise through Chapter 8, get that knocked out. And like I said, that exam should be open about 3 this afternoon. Anybody have any questions on anything that we went over on Chapter 7 on Tuesday, or are we good to move on? All right, I'm going to jump right into Chapter 8 then. Let's see. So, Chapter 8, oil and gas engines. Maybe. All right, so we basically have 2 different types of engines, and we've touched on them a little bit as we go here. But what are the 2 different types? How do we external and internal? When you think of your car engine, what kind of an engine is that?
Internal.
That's internal, right? The explosion is all contained inside. It spins moving parts and takes that converts the energy from that explosion into rotational energy to turn your wheels. So what's an example of an external then? It's actually what we started out with years ago. Yeah. External combustion is basically you have a fire that heats water, some other fluid to create steam to do work. So basically the fire is outside the machine. So I've got my pot of water here, and then underneath it yeah, see, that's that so I got a fire down there, heats up that water, steam comes off. See, that's that ceramics degree paying off right there. We capture that steam. It goes into some sort of device that has a piston inside. And that steam, as it comes in, pushes the piston and gives us our force, right? To do whatever we want to do with it. So now if I want to do the same, if I want to spin something, if I use an internal combustion, basically the only difference is the fire is inside. So I'll have my combustion chamber here. My piston right here attached to a crankshaft or whatever. My fuel comes in, the actual combustion happens right here, and my exhaust goes out. As what happens when fuel burns? What does it do? What's the idea behind it? It fires when it's compressed. The force of that stuff burning, it expands, and that expansion drives the piston down. So where did we start off at? When we first started doing engines, we came up with ideas for engines. How did we get started on that? Any idea? What was our first attempt at machinery? External combustion, right? And we've seen some examples of that. We used them for pumping water or whatever. We're just looking for a heat difference to force a piston to do something to make it do what we want. So then we get into what was our main delay of why we couldn't get started on internal combustion engines right away? Why wasn't that the first thing that we invented?
Gas wasn't available.
Yeah, we didn't really have a good fuel.
Didn't have ways of casting.
Yeah, mostly it was mechanical. We didn't have the metallurgy. We didn't have the quality of iron and steel that we needed, and we had no way to make those tight tolerances that are required. Internal combustion engine, everything has to fit really tight in order for it to work. You'll find out right away if you have a problem in your car engine with a head gasket or a blown ring or something like that, because those tolerances are so tight, it's just not designed to work if you don't have those tight tolerances. So we got started, and there's a couple different kinds. Germany, Nicholas Otto kind of did the first thing, kind of had the first engine, and let's see, by 1876. So we're kind of well into the Industrial Revolution, right? And we've been using steam engines for a little while, but we had a lot of problems with explosions, again, because of that metallurgy. So by 1876, he kind of figured out a good way to make the thing go. You have to have the right mixture of fuel and air. It has to be compressed, and then it'll expand and turn the engine. Now, what's kind of neat is the first thing that they came up with was actually a diesel engine before they came up with the gasoline engine. Diesel engine doesn't use a spark, doesn't use anything. What sets it off? What makes it go boom? Compression, right? The compression is so high that you got so much fuel and air crammed in there. As it compresses, it squeezes it, and it just can't, all that friction of those molecules rubbing against each other, when it hits a certain point in compression, they detonate, they go off, they start on fire. And that creates our power stroke, the expansion of those gases. So it's actually a pretty simple design. But it was a two-stroke. What's the difference? We'll talk about that a little bit. What's the difference between a two-stroke and a four-stroke? What's that?
Valves and it. I can't think about it. Remember, intake, compression,
Exhaust. Everything kind of all happens at once, right? It all happens in one stroke of the piston. If you look at the figure 8.3, but on page 279, you can see it's a very simple engine. It's simply the shape of the piston that allows this thing to, it comes up, it compresses the fuel air mixture, the spark plug sets it off. On the exhaust stroke, as it comes down, because of the shape of the piston, the exhaust valve or exhaust port is open before the intake port is. So you have all these hot gases that are still trying to expand. They go out, hey, look, there's an opening. It's easier to go out than it is to push the piston. So they all evacuate the chamber. As the piston goes down just a hair farther, now all of a sudden the transfer port where you can get fresh fuel and air in there comes in, and that flows into the vacuum created by the exhaust leaving, refills the chamber. As the piston comes back up, it compresses it, fires, and it goes again. So these things run at a really high RPM typically, but they're not very efficient. Why aren't they very efficient? Any ideas just by looking at that?
Friction.
Yeah, friction a little bit. There are less moving parts though, so there would be less friction applied to the system overall by not having valves and cams and stuff.
The two-stroke is less efficient?
Yeah, the two-stroke.
Oh, yeah, because it doesn't really have a way to control fuel and mixture and stuff.
Right, it's not really, if you look at it, the fuel actually goes through the crankcase first.
Yeah.
Because there's no separate oiling system within the engine, no oil pump or anything like that. The oil is mixed in directly with the fuel to lubricate it. So it goes into the crankcase first, and only a small portion of that oil actually does what it's supposed to do and oil the bearings. But you got to have enough in there to make sure that it gets plenty of oil. So the oil, does the oil burn in that during that explosion? A little bit, not really. I mean, you'll get a pretty good smoke cloud out of it, but it's not. We know how gasoline burns compared to diesel fuel burns. It takes longer. For the heavier that oil is, the longer it takes to burn. Well, if you've got this engine turning 18,000 RPMs, how long is that oil in that cylinder under that direct flame? Not very long. So typically, it's very, very dirty, and you get a lot of oil coming out of the exhaust. It's not a very efficient burn. And it's also because not all the exhaust goes out. Sometimes, depending on how the mixture is, or the timing of it, you may have some raw fuel and air mixture going out the exhaust port to make sure that the thing's full. You're going to put in a little bit extra. So it's not very efficient, fuel efficient wise. They are crazy powerful though for their size. Anybody ever rode a motorcycle that's a two-stroke compared to a four-stroke? Boy, hang on to your hat, because those things are exciting when they go. With that high RPM, there's a lot of power there, but the efficiency's not near there. That's why, and that's where the pollution comes from. So then we go to the four-stroke engine. If you look at the four-stroke engine, it has 4 different strokes, which is why we call it a four-stroke, and that's in Figure 8.2. That one has valves, so you can control each one of those steps easier. There's much more control over the fuel air mixture. There's much more control over where it's at what stage. So it's much more efficient, fuel efficient. So you have an induction stroke where the inlet valve opens up, the exhaust valve is closed. As the piston comes down in the cylinder, it creates a vacuum in that space, which draws the fuel in. The inlet valve closes, the piston comes up, it compresses that fuel in there. That's the compression stroke. You have the explosion where the spark plug sets off the mixture in there, which gives us our power stroke, forcing the piston down. And then the next time as the piston's coming back up, the inlet valve is closed still, but the exhaust valve is open. So now it comes up and compresses and pushes the exhaust out. As soon as the exhaust is all out, and the piston's hanging out right there at the top of the cylinder, that exhaust valve closes, the inlet valve opens, so now when the piston's coming down, it's drawn in the next batch of fuel. So there's 4 separate steps to it, and that's why it's called a four-stroke. So our cars, for the most part, now have 4 strokes. In the United States, they pretty much all have 4 strokes just because of emissions. There are still some places in Asia, I believe, where they still run a lot of 2 strokes. And you can see that a lot of those they do the little 3-wheeled carts, like the 2 wheels in front and 1 in the back, and you'll see those things going along, just smoking, huge cloud of blue smoke out the back of them. That's because it's a two-stroke engine. One of the big things, the big technology, the other thing to figure out was a carburetor. What's a carburetor do?
Regulates the fuel.
Yeah, it regulates the fuel going in, and it's kind of an air-fuel mix, right? Well, you can pour straight gasoline into an engine, but what does it do? What's that? It'll flood it, right? There's an ideal mixture that we're looking for. It's called stoichiometry. And what we're looking for is that air to fuel ratio. If it's not in that proper mix, gasoline won't burn. We know there has to be oxygen present, we know there has to be fuel present, and there has to be some way to initiate that fire. Well, just a puddle of gasoline in there, the only thing that's going to burn is the vapors off the top. The actual liquid gasoline won't burn. So the carburetor makes up for that, and it actually mixes the meters, I guess you could say. It meters the fuel coming in and the air coming in. And nowadays we deal with fuel injection mostly, but the carburetor actually has jets in it that create a fine mist of fuel into that air coming in. Ideally, will meet that correct stoichiometry for the most optimal burn. Any guesses to what that ratio might be? It depends on a lot of things. It depends on altitude, what your air density is.
Have 18 psi on a turbo on a car that doesn't need it. There's
Right.
But it's probably like 14.7.
Yeah, it's actually very, very close. About 14.7 to 1, which means you need that much air, that many units of air to 1 unit of fuel for the proper mixture. And we talked about on Tuesday that 1975 truck driving down the street with a big cloud of blue smoke coming out, and you can smell the gas fumes in the air.
So it's probably like 10.
So he's at probably, he's way high on the fuel ratio in there, which results in unburned fuel. What happens if you go too lean on it and you don't have enough air in there to go with the fuel?
Burns super hot.
It burns super hot because that air also acts as cooling as well. It burns really, really hot, and you end up burning a hole in your piston. So lean is not good. Rich is safer than lean, but also not good, especially not if we're looking for efficiency.
And if it's too rich, you can wash
It washes the cylinder walls.
it won't create compression anymore.
Yeah, because in a four-stroke engine, the oil system is separate. It's down the crank, and it just kind of splashes everywhere. And the oil pump does inject it into certain places. It is a pressurized system. And what happens is as your piston moves up and down, there should be oil on the walls. And the rings ride on a very, very thin film of oil up and down to reduce friction. Well, if you get too much fuel in there, it washes that oil off there, and now you got bare metal on your rings, and it will destroy your rings, and you lose compression, and the engine stops working. So the carburetor was a huge deal. They were playing with it in the late 1800s. Carl Benz, we kind of recognize that name, right? From Germany, 1886, he had a three-wheeler car with a petrol engine. He patented it. 1893, they had a four-wheeler with a 3-horsepower engine. Go 18 kilometers an hour. So, which is about 12 miles an hour? Not real fast, but beats walking.
Yeah.
Definitely beats walking, right? And then the French have been playing around with steam cars, which is what kind of engine? External combustion, playing with steam. And what's the huge advantage over a petrol engine or gasoline engine compared to a steam engine? If I get up in the morning to go to school, what do I have to do if I'm going to drive a steam car? Got to get a fire going. got to get a fire going. I guess it's pretty sweet because you
boil
could.
water, essentially.
Yeah, you could.
Orphan.
So you could probably tap some coffee off of that while you're at it, but you're gonna need an hour to get a good fire going to build up to boil water, so you got enough steam to go, 12 miles an hour to school. And you can imagine how bad Missoula would stink if we were all burning wood or coal in our cars. It wouldn't be good. So, needless to say, the gasoline engine. Now, if I get up in the morning and I'm going to go start my gasoline engine to drive to school, what do I have to do? Turn the key, start it, put it in gear, and go, right? I mean, it's instant. So the convenience of it. Now, while I'm sitting here at school all day, what's my gasoline engine car doing? Just sitting there. What's my steam engine car doing?
Cooling down.
It's cooling down. You got a fire going for no reason. You got steam that's just going to be venting off until the fire goes out. So I get ready to go home. I got to go start the fire again, reheat the water for another hour, and I can drive home. So it's needless to say, it's pretty obvious why the gas engines came into being. 1890, Daimler. There's another name we know from Daimler Chrysler nowadays. So 100 plus years later, the guy's name's still in the business. 24 horsepower in 1904, double-decker motor bus. So you can imagine that would be pretty heavy to run on 24 horsepower. That's pretty impressive. Probably not very fast, but they debuted it in 1904. In 1913, there were 2,000 of them in England. So it had all been horses, and stuff up until that time, and now all of a sudden there's cars rolling down the road. So wow, there you go. And then they decided, okay, let's bump up the power a little bit. Why would we want more power? What does more horsepower give us? What's the advantage of having more horsepower? Increased speed, right? So I'm going to travel faster. And we're going to get into the math of that a little bit here, of power and speed. But it's crazy. We're talking here. They wanted a new car in 1900. Mercedes. They named it after his daughters, Mercedes. And we just talked about Benz just a minute ago, so obviously they had something going on there. So they did the Mercedes passenger car. When it's first raised, it had 56 kilometers per hour, so probably 38, 39 miles an hour, something like that. About the speed we drive down Orange Street here or Brooks. Very expensive. 2 years later, they had the 60 horsepower model, which would go over 60 miles an hour. And if you strip it down for racing, it'd go 70. So screaming right along, right? But it's funny because we still look at that today, of how much horsepower does it have? It's something that's still today. Will a car, let me see, how can we phrase this? Would a car that has 60 horsepower today, could I take that out here on the freeway on I-90? Yeah, a lot of it depends on weight, so we're into the mass thing, right? But if I kept it fairly lightweight, how much do the old Volkswagen Beetles have for horsepower? Any idea?
60.
About 60, I think. Yeah.
That's Super Beetle.
Okay.
It's like 73.
All right. So, but they'll do 75 miles an hour as long as there's no headwind and it's flat and everything, all right? How long does it take them to get up to 75 miles an hour?
It's like 17 seconds.
It takes quite a while, right?
The Beetles are actually funny. They have a longer 0 to 60 times, and they're quarter mile, I think.
So they're not even going
They're not
60
going
miles
60.
an hour when they hit a quarter mile.
Yeah, they're not even going 60 by the end of the quarter mile. It's really funny.
So our average car out here in the parking lot, if I decide, okay, there's a stopwatch on me, I'm going to see how fast it'll go 0 to 70. How fast are these cars going 0 to 70?
8 to 10.
8 to 10 seconds, right? Pretty quick. And probably less than a quarter of a mile. So that's where that horsepower makes a difference, is not necessarily in sustaining a speed on the highway, because once I get up to 70 miles an hour, how much horsepower do I need to maintain that? Not a lot, right? The 200 horsepower I have under the hood is to get me from 0 to 70, not necessarily to maintain 70. So, and it's all about, if you look at box 8.2, it's all about mass and kinetic energy. And so if we look at, figure the average car, I think they use 1,000 kilograms, so 2,200 pounds, which would be a fairly small car, fairly light car. We already know about kinetic energy and how to figure it out. It's 0.5 times the mass times the velocity squared. So 1 kilogram traveling at 1 meter per second has a kinetic energy of 0.5 joules. So we figure we can just throw in those numbers for the car, 1,000 kilograms, and we're going to say it's 30 meters a second, which is about 70 miles an hour. We were talking about how fast it would take our car to get there. So that 30 squared times 0.5 is going to give us 450,000 joules, 450 kilojoules. That's our kinetic energy. That's how much energy is stored and moving in that car at that speed. So we can also do a calculation of, I guess we are talking about the Volkswagen here. If it's designed to reach that speed in 20 seconds, we can just divide our 450 kilojoules by 20 seconds. And if our car has about 30 horsepower, it will accelerate to 70 miles an hour in 30 seconds. So if I want to accelerate faster, now I want to accelerate in 10 seconds instead of 20 seconds, what number has to change in there? Yeah, my weight or my horsepower, right? Well, our weight's pretty consistent. We've decided that, yeah, that's about the size of the average car. Maybe a little bit light, but that's about right. So I need to double the horsepower. So I'll just throw my car out there as an example again now, is I know it's 200 horsepower. I'd say it's probably pretty accurate that it takes me about 20 seconds. Or no, I'm sorry, it takes me about 10 seconds to get up to 70 miles an hour. So if I throw those numbers in there, and this equation doesn't work, this equation says, wow, you should be doing it in like 4.4 seconds. Where's the difference at? It's going to be in the weight, right? It doesn't weigh 2,200 pounds. It's probably more like 3,000 pounds. So as those numbers change, so does, if any of those numbers change, whether it's the rate of acceleration, the total speed, or the mass, the horsepower is going to be affected one way or another. So they are all. So now we talk about climbing hills. And this is kind of where we're talking about, on flat ground with no headwind or anything like that. So now gravity falls into play, right? Because we're climbing a hill. So now, again, we know the formula for figuring that out: mass times gravity times height. So we know here we're talking about you got to climb a 1 in 20 hill, which means for every 20 meters forward you go, it climbs 1 meter. And that's 100 meters high. And we're only going to do it, let's see, 60 kilometers an hour is 40, 42, 43 miles per hour, something like that. But we can just plug our numbers into that equation. We know our mass is 1,000, it hasn't changed. Where did the 9.81 come from?
Not just the standard gravity.
That's the force of gravity, right? And 100 is how high we're going to climb. That's our height, right? 100 meters. So we do that math, and it's like, okay, that's the energy needed is 981 kilojoules. We talked about on flat ground, the energy needed was 450. So literally, it's over double the energy required to be able to climb that hill and maintain that speed. Let's see, and they're doing the math, continues along. We know we're going to go 2,000 meters to go that distance, right? Because it's 1 in 20 ratio. So to go 100 meters, to climb 100 meters is going to be 2,000 meters. 60 kilometers per hour, it's going to take about 2 minutes to do. So now we can convert it to kilowatts. Our 981 kilojoules is the power required to climb that hill. It takes 120 seconds or 2 minutes. Give us 8.2 kilojoules per second or 8.2 kilowatts. And it's kind of funny, just as a side note, they're talking about going down a hill. It's kind of the opposite. And this is something that electric cars really take advantage of, because if I'm going down a hill in my 1-ton truck and I push in on the clutch and I'm just letting it free roll, but I need to keep my speed at 70 miles an hour, how am I doing that? I'm braking, right? What does a brake do?
Provides friction.
Provides friction. So it takes rotational energy and converts it to heat. That's all it is, just a big heater, right? Causes that friction, which causes heat, which bleeds off into the atmosphere. How does an electric car, how do the brakes work ideally? Not always, but how do they work on an electric car?
Recharge the batteries.
They recharge the battery, right? We have an electric drive motor that accelerates the car and gets it up to speed. So if I use that motor for braking, engage it, spin it backwards, use let that absorb the energy. It's still rotational energy. It's just spinning the motor backwards. What happens when you spin an electric motor backwards? It's a generator. So now it's putting energy back into the battery. So it's regenerative braking. Instead of losing it as heat, we can capture that energy.
So do the brakes not get warm then?
What's that?
Do the brakes not get warm? How does it actually?
I've not looked at their system. I suspect that they have the regenerative braking, but I suspect they also have regular brakes as well. But I'm not sure. I've not looked into them enough to know.
Oh, does regeneration more like work through the transmission?
Yes.
Oh, okay. Okay, that makes sense. Because I was like, how?
It's like engine braking, not actual.
Yeah, it's the same thing
how
as.
is it like going through the brakes, collecting the heat off of the brakes?
No, it's not collecting the heat off the brakes.
Okay.
It's
It's
spinning because there's an electric drive motor on each wheel, right? Or there's one electric drive motor going through a transmission.
Okay, that makes sense.
So now, instead of braking, if I let off the gas, the car assumes I want to slow down, and the car will slow down because I'm not applying force to it anymore. As that deceleration happens, we can just spin that motor backwards, and now it's a generator. It's generating electricity to put back in. I think for emergency braking, they probably have regular disc brakes as well, which are the old school heat. But that's something that we're playing with all the time. What else plays into the to my car going down the highway at 70 miles an hour? Theoretically, we know the exact numbers of how much power it takes for me to accelerate and to maintain that speed. What other factors and everything so far is assuming a perfect world. But what other factors come into that? How much power? aerodynamics are huge, right? If you put the modern passenger car nowadays in a wind tunnel, they measure the air resistance. They're actually very, very aerodynamic, right? What happens if you put like a 1957 Chevy in the wind tunnel? It's a brick, right? I mean, there is no aerodynamics. You know, if we look at that school bus parked out there on the road, and then we look at any one of these cars parked next to it, they could probably both go. You could probably use the same engine in either one of those vehicles, right? The car would get its 35 miles per gallon or whatever it does. What do you think that bus would get for mileage using the same? You might get 5, you might get 8, right? That's why you see these giant motorhomes cruising down the highway. They're getting 5, 7, 9. A really, really efficient one might get 12. Yeah, it's not so they can go really, really far. That's just so they can get to the next gas station, right? Because there's a brick going through it. It's that aerodynamic drag. How much, what about what are some other forces that affect it?
Road surface.
Road surface?
Friction from the tires to road.
Yeah, friction from the tires to road. If my tires are at 40 psi, they have a certain amount of rolling resistance, right? There is still some resistance. It's not ideal. I'm losing some energy to the road surface from friction. But what happens if my tire is at 20 psi on that same car? Creates more friction, right? More drag, which increases the power requirement, and it kills tires. Because what does that increased drag cause? Heat. Causes heat. Your tire overheats. It literally comes apart and will disintegrate on you. So that's an issue. We've got stuff there. How do they measure the horsepower of a car engine? Where do they typically measure it at? Right at the crankshaft, right? They have the engine not in a car, just sitting in a test stand on a dynamometer, which measures horsepower, and they spin that dynamometer and they get a great number, and they're like, whoa, this car has 200 horsepower. If I were to put it on a rolling dynamometer, where you roll the car onto it, strap it down, and the wheels are on top of the same system as a big drum that the wheels spin, and it tells you how much horsepower it has, what would that 200 horsepower car have sitting on one of those dynos?
Like 160.
Probably, yeah, like 160 or something.
You lose like 10 to 15% through your drivetrain.
Okay, so I've got losses through my drivetrain, right? Because we know it's not aerodynamic. So I've got losses through my drivetrain. It takes energy to spin that transmission with all the fluids in it that are being circulated around. It takes energy to spin that drive shaft. Then it has to go through a differential. All those things have friction in them. All of them have resistance in them. And by the time it gets to the wheel, you don't have 200 horsepower. You have 160, or whatever it figures out to be. Each one's going to be a little bit different. But there is a considerable loss. All those things come into play of how much horsepower do I need to make my car cruise comfortably 70 miles an hour down the highway, and what's the most efficient. Accessories. Then this one's actually kind of a big one, and it's kind of cool. The more I study it, if you look at a race car, what kind of accessories do they run off the engine? They have like a AC compressor on there, and they don't have all the junk that we do on our car. Typically those engines, because that's a parasitic loss, they're losing power turning that belt to turn whatever those different things are. If you look at modern cars,
Like we don't have like fan belts, that kind of hoopla. It's electric fans.
right, we use an electric fan instead of this big fixed, metal fan out there mounted on the front of the water pump, right? Because that electric fan, now I can control it and I can optimize my operating temperature for my engine. If it's really hot outside, the fan might run all the time. But what if it's 20 degrees out and I'm driving 70 miles an hour down the highway? Does that fan need to be spinning all the time? No, not at all. Probably just the airflow alone is enough. So we get rid of that parasitic drag off of the engine. A lot of cars now, it's the past 40 years, you pretty much can't buy a car that doesn't have power steering. And the power steering pump is parasitic. It's taken energy off of the engine. Those have changed over to an electric pump because now it only runs when you need it to. And we've gotten rid of the parasitic. That's where really the technology in the engines has not changed that much. We're still using the same basic engine block and same basic engine design that we were using 100 years ago. What we figured out is all these little things here that we can take off. If I make the car more aerodynamic, if I take off the parasitic loads, if I make it a front wheel drive, now I don't have all those drive shafts and stuff to deal with. I can get rid of those drivetrain losses, and it just makes it a whole lot more efficient. So, all right, page 284. The U.S. is where really cars took off. That's like our claim to fame. If you look at any country and what are they famous for, the U.S. is the automobile, right? We have huge distances to travel. It's freedom, and everybody knows we love freedom, so you need half a dozen of them in your driveway because that's freedom right there. So, and a lot of it was Henry Ford with the Model T. He kind of invented the assembly line and made it so instead of these rich people saying, hey, I want a car named after my daughter, we'll call it a Mercedes, we're going to pay you a ridiculous amount of money, this guy figured out, hey, I can make cars for $850 because they're all the same. They're all black. They all have the same exact engine, the same exact interior. Everything's the same. And mass production, I can make them cheaper. So that's kind of where it really took off. He had the first assembly line in 1913 and cut the construction time per car from 12 hours to 93 minutes. So that's cruising, right? And that's a very simple car. But still, they were able to cut it down to an hour and a half to build one of those. Well, you're paying
to assemble it.
Yeah, to assemble it.
Not the big parts.
So you're making your employees are getting paid by the hour. So there's a huge difference between paying them for 12 hours of work to build a car and for an hour and a half to build a car. So you see where
got away with paying them less because when they started, it actually took an educated person to build it. And when the assembly line came, all you had to do is do your one thing.
Yeah, you don't have to know how a car works. You just know that
Exactly.
this bolt goes here,
And I typed.
and that's all I do every
So
day.
they made tons of money off of that too.
Right. And how long now, even so we look at that car and how simple it is, we look at one of these cars out here in the parking lot, how long does it take them to go through the assembly line?
Not very long. It's a lot to build it.
Probably about the same amount of time. It's probably about an hour and a half, but it's just assembly. It's all the pieces already made, and there's just huge warehouses full of engines and tires and frames and body parts, and literally it's just going down a line. Talk about airplanes. Airplanes really came into their own because of gasoline engines. Because can you imagine trying to fly an airplane with a steam engine? They don't produce enough power. The power to weight ratio is crazy. The fuel is inconvenient. Then really, are you going to have somebody in the back of the plane shoveling coal, into your boiler? Just kind of not really conducive.
Make sure
But-
it's still hot enough.
Yeah, you don't want that one running out of steam, right? That'd be a bad thing.
Yeah, it's not like a train where it just stops on the track.
So if you look at the Wright brothers, they had to build their own engine. It's not like you could go out and buy an engine to do it. They built their own lightweight 12 horsepower 4-cylinder engine. And it was kind of cool. We're talking about those air fuel mixtures, right? Airplanes run into that issue that even here in Missoula, when before I retired, I lived in California right on the coast. So I'm at sea level, right? My motorcycles are tuned to run at sea level, and they still have the basic simple carburetor. I moved to Missoula, and I'm at 3,300 feet of altitude. Is that still putting out the ideal mixture? Nope, not at all. I had to go into my carburetor and change the fuel jets. Well, that's great on a motorcycle where you're really not. I've got, probably a 6,000 or 8,000 foot window that I can work in. I'll notice a loss in power because of less oxygen in the air, but it'll still work. But is that realistic for an airplane to be able to change the air-fuel ratio while you're flying? You can't do that, right? And because you can be at 0, you can be at sea level, and 10 minutes later you're at 10,000 feet. That engine doesn't run the same. So they came up with superchargers. What's a supercharger do? Any idea? This forces more air into the engine. We know we need, if there's less oxygen in it, I need more of it to still have that same ratio of oxygen molecules. So they figured out superchargers, which just means I'm blowing compressed air into that. Literally, all it is an air compressor. I'm blowing compressed air into that engine so it has enough oxygen to run. And they also figured out the turbocharger, which the supercharger runs directly off the rotation of the engine. A belt turns that compressor to supercharge the air. A turbocharger runs off the exhaust. It spins a turbine, which compresses the air, does the same thing. And they were able to do it, on airplanes, and we figured out, well, hey, let's do it on cars too. And pretty impressive, pretty amazing when you look at aircraft engines for the weight and the size of them and how much horsepower they can make. And of course, war, we just want to, how can we make something faster so we can kill people faster? It drives that. So you're talking, the World War II airplane engines were amazing. A 27-liter engine. These things are putting out 2,800, 3,000 horsepower. And they're, heavier than a car engine, obviously, but not a whole lot. They got some pretty amazing efficiency out of those. All right, where are we at on time here? All right, I'm going to stop this one, and we'll start another one so we don't go over.